goes over time. I'll race you Mario Kart.
All right, let's take a look. So,
It's Mario
click them all the way closed. I'm gonna give you a chance to do some work today. But I do want to just kind of wrap up a couple of thoughts here. So we covered a lot of ground yesterday. We talked about continuity on intervals, and I feel like we need to revisit that just a little bit to make sure everybody's feeling 100% there. So when we talk about somebody, just in your own words, what's it mean to be continuous from the right?
There's no holes coming from the right.
Okay, coming from the right, there's no holes, and so, like if I'm on an interval, if an ant's walking, and think about this in terms of our calculus ant, right? Calculus ant is only on firm ground. You can only step on places where the function is continuous. If there's a discontinuity, that's gonna be a major obstacle for our ant. If it's an infinite discontinuity, it's an infinite mountain you can't pass, right? If it's a hole in the function, he doesn't wanna step there, because he's gone, who knows where he goes, right? And so, from an ant's perspective, on an interval, it's continuous from the right if he can walk all the way up to the left boundary and stand on it. Agreed?
Yeah.
That make sense? Okay. Continuity from the left would mean if he's walking from the left.
I just need to snag it
The team room key?
Yeah.
Okay, you bring this right back to me?
Yeah. Yeah, I forgot.
Oh.
So.
Yeah.
Beaver.
I think that's it. I think it's that one. I think it's that one. Okay, so continuity from the left then would mean an ant can walk along towards a right end point from the left and stand on the end point. Make sense? Okay, and we have to have this because if we're going to define continuity on a closed interval, we can't just rely on, oops, that's frozen. Can't just rely on our criteria for continuity at a point, because in general, they expect us to be able to take a two-sided limit there. We can't do that at an endpoint, right? We can only take a limit from the left or a limit from the right, okay? Okay, so what about continuity on an open interval? That's a strange concept. What if we want to talk about continuity on the open interval from A to B? What does that mean? Is it including the endpoints?
No.
No. What's it saying though?
In between these points, it's continuous.
Okay, in between those points, the function, all of the infinite points between A and B meet the three criteria for point continuity, right? So you can, and would you agree, and this, once again, this is kind of you gotta put yourself in this mind frame, but for all values greater than A and less than B, there is no endpoint, right? So I could get arbitrarily close. If the door is my limit here, I can get arbitrarily close to the door, and there's still an infinite number of points between me and the door. So I'm not including the door, but every point this side of the door is on a continuous interval, right? So when we say something like, I think there's one place in here, I want to underline one word. Okay. A function is continuous over an open interval if it is continuous at every point in the interval. In the interval means greater than A and less than B. Agreed? And so then, all we have to do to extend that to continuity on a closed interval is say, okay, so it's continuous on the open interval between A and B, and we have continuity from the left at B and from the right at A. And all of a sudden now we've got continuity on a closed interval. Okay, make sense? All right. Okay, so then this is where we left off yesterday. And there's a bunch of problems that I'm going to throw at you on this assignment. These are good assignments, really good assignments. I'm very, very proud of these assignments. I think the problems are right on. So there's some challenging ones in there, but they're doable. State the intervals over which the function is continuous. So this is where I want to go back and do a little review of analysis, because this is something that I think is really a big deal. This is a big point of emphasis, I think, in pre-calc, really, just elementary analysis, right? So how do we deal with something like this? Well, what's the domain of the function first? We gotta figure out what's the domain of this function, right? And inside the domain, there's nothing crazy going on. It's gonna be continuous everywhere in its domain. There's no crazy jumps in a square root function or anything, right? But where is it defined? What's its domain? So this is where we gotta think about the two fundamental no-nos for real numbers. We can't divide by zero, not an issue here, and we can't take an even root of a negative number, right? So we left off yesterday saying, okay, well then, whatever the argument of the square root function is, just don't confuse yourself by even looking at what it is. Whatever is inside, has to be non-negative. So that allows us to set up an inequality that's gonna, when we solve it, gives us the domain. It's just magical that way. It's really cool that math works that way. You make a logical statement and you're asking the math gods for information, right? When we set up this inequality, we're petitioning them to tell us what values of x make this true, which is our domain, right? This comes directly from that one rule. We can't take an even root of a negative number. So we just gotta solve this thing. So let's go through the algebra. How do we solve for x in that inequality?
Subtract 4.
We can subtract 4, that's fine. How about if we just add the x squared to the other side, so we don't have to worry about flipping it? Okay.
Yeah.
Okay. Either way, I mean, your way would have worked too, would have been fine. But then we gotta remember to flip that inequality when we multiply by a negative. So we're just gonna add the x to this side and then let's reverse it. Say x squared is less than or equal to 4, right? Now what? Square root of both sides. What's that give me?
2. Plus or minus 2.
Okay, be careful with this. This is the
We
one where,
talked
this is
about
that missing step that you guys are used to glossing over, but you can't do it necessarily when you're using inequalities, right? So if I square root both sides, on the right I get 2. What do I get on the left? Absolute value of x. That's the step you are not accustomed to, right? So the square root of x squared is the absolute value of x. And that's less than or equal to 2. Where's the plus or minus you're saying? It's not there yet. It comes from solving the absolute value, normally equation, but in this case inequality, right? So now what? How do we solve an absolute value inequality? If I have an absolute value of something is less than or equal to a number, how did that has to translate into a compound inequality? Is it an and or an or? Conjunctive or disjunctive? Which one? Not or. How come? How come? I'm going to show you a way to remember this. It's and, but why? There's a couple ways you could kind of finesse through this a little bit by just saying the absolute value of x. There's a couple ways we could look at this, and they're all consistent. So one way that I think would be good, how about this? If we say this is 0, what is the absolute value of 3? 3. What's the absolute value of negative 3?
3.
Okay, now let's look at where those are on the number line. Here's 3, and here's negative 3. What about both of those values seems like it ought to be 3? The distance from 0, right? So this is negative 3, and that's 3. And the distance from 0, the distance from the center of that spread, which is 0, is 3, right? Okay, so if you're asking the question, for what values of x is the distance between x and 0 less than or equal to 2, where's that going to be? I mean, that's going to be an and statement. That's going to be all the values in between those endpoints, right? You see what I'm getting at?
Yeah.
Okay. So negative 2 and 2 and 0, it's got to be, those are the values within 2 of 0, right? Now, if I wanted to know where is the absolute value of x greater than 2, then I want to know all the places where the distance between x and 0 is greater than 2. Well, that would be everything out there on that tail and out there on that tail, okay? So that's an easy way to remember that. Sometimes it gets a little confusing when you've got a bunch of stuff, when you're solving an absolute value inequality, you have a bunch of stuff inside the absolute value bars. But later on in the course, I'll revisit that and remind you that we can just make a variable substitution and choose a different variable space, and it would look just like this, right? But just think of it in terms of this simple model and generalize. That works a lot in math. I can't tell you how much I did that in my brutally hard math classes in college. Just, okay, I'm gonna make a really simple example and then generalize to something much harder, and the pattern, it's much easier to see the patterns, right? So think of it in terms of this simple example, and you'll never forget that. Here's another way to look at it. What if we were to, on the xy plane, let's look at the graph of the absolute value of x. What's that look like? My graph, y equals absolute value of x. It's a V, right? It's a V with the vertex at the origin, and it just does that, right? There's the absolute value of x. Okay, let's graph the function. Well, how about if we just take 2 as an example, being as that's what we looked at isn't that the last page we looked at? 2. Absolute value of x is less than or equal to 2. Okay? So y equals 2. How do I graph that? Straight line at 2. So there's the line y equals 2. Okay, now, if I want to know where is the absolute value of x less than or equal to 2, well, the absolute value of x is the output of my function, isn't it? That's just a y value, right? So I'm wanting to know, where are the output values of this function? Where are the values of this function less than or equal to 2? Well, in the xy plane, when we talk about lesser y values, what directionality does that describe? Yeah, down, right? So we're going to take everything, like this is like a water line, and we're just taking everything below that water line, right? Well, where is that? Where's the intersection of that half plane with our red absolute value function? It's happening right here, isn't it? It starts there and it ends there. This is the part we're talking about. And so if I'm looking for, that's where it occurs in the xy plane, but really all we're looking for in this is just the x values, right? So if I map that down to the x-axis, there's a point at negative 2, 2, there's a point at 2, 2, and if I map that to the x-axis, it just looks like that, doesn't it? Yeah, same deal, right? Multiple ways of kind of looking at the same problem, but now you have a concept, because you're going to forget, when I first asked you, is it an and or an or, you tried to just remember it, right? I mean, and you're going to forget that by state capitals. You're going to forget that stuff. Everybody does, but you're not going to forget the concept, because the concept is attached to so many bigger topics that you don't forget, right? Okay, moving forward. So this becomes an and statement then. So what's that look like? What's that look like if I solve this then? X is what? And there you go. Okay, so that's our domain of this function. That's where this thing is going to be continuous, right? X has to be greater than or equal to negative 2 and less than or equal to positive 2. Yes?
Could you write that in interval notation if you wanted to?
Sure.
Okay.
Yeah.
I didn't know if that was like the form you wanted it in,
No,
or
that's
we
good.
could write it.
That's good, yeah. So, make sense? Okay. All right. Okay.
So did we answer that question?
We did.
All right.
So the answer is the intervals would and let's just look at this thing in Desmos just to verify that we're on the right track. me know. Okay? Does this function, does it exist? Like if I do f of -2, whoops, that's undefined, right? If I do f of -2, it tells me 0. Okay, if I try to do f of -22, it's undefined. But it does exist there, so those endpoints are included. So an ant can walk towards the left endpoint from the right and stand on the left endpoint. So we do include that, right? Does that make sense?
Yeah.
Okay? All right. There's a little shortcoming with, and I'm going to harp on this all year, but what's one of the shortcomings of using a graphing utility like this? They're amazing, and you're going to be Desmos experts by the time you're done with the class, but what's one of the shortcomings of this?
You don't feel all
Well, okay, I mean, but I'd say most of the time you'll have to understand the math to make the picture, but what about that picture is just a little bit unclear? I'll give you another example. What about, I'm going to graph another one. What if we do g of x equals x squared divided by x? What's a little bit unclear about that green one? What points are included? Yeah. Well, what's the only number excluded from the domain of g?
0.
0. Okay, so if I do g of, of 0, yeah, it's undefined, but it doesn't show up on that graph, does it? See what I'm saying? So things like, sometimes features of the graph, thank you, sometimes features of the graph that are really important, holes in particular, all they show up on a graphing utility, all they show up as is just a missing pixel, maybe, that you're never going to see, right? So you still have to be aware of that stuff, right? Okay, I'm going to let you work.